All right, this morning I was thinking about the rest of the semester and plans were solidifying in my mind about what we should do. And so, yeah, like I mentioned, today and probably through at least next Tuesday, we'll continue with this kind of theoretical stuff that does have applications related to estimation, confidence intervals, hypothesis testing. My goal is to get through something called the Neyman-Pearson lemma and likelihood ratio tests, just focusing on the basic idea through the context of examples. The topics could have much more depth to them with a lot of theory, more theory even than we do. We want to just get an introduction to them. After that point, I think it would be good to do some work with categorical data and something called chi-squared tests before exam 2. And then transition into regression, both simple linear regression and multiple regression for the rest of the course. And that's where we'll make use of R, is in that part for the rest of the course. So that feels right. It doesn't quite match everything that we had as a goal in the syllabus, but again, that was kind of aspirational anyway. So I think that'll be fine. Also this morning, I was experimenting with the content for today and using Mathematica, and I came away once again amazed at the things that Mathematica can do, some things that I wasn't expecting it to necessarily be able to do. And so hopefully we'll be able to make use of that today as well. So we're going to start with an example. And the example actually is stuff we've done before, but it's just a new example. The stuff I'm talking about that we've done before is the method of moments and method of maximum likelihood. That would be good to review, especially maximum likelihood, because if we're going to understand this Neyman-Pearson lemma and likelihood ratio test, we do need to think about the likelihood function again. Okay, that's going to come into play again. Also, after that point, hopefully we can quickly review some things about confidence intervals and review what you know already about hypothesis testing. Not sure how much time we'll have for today. For sure on Thursday, we'll get into those details. So let's look at an example. The example we're going to consider is going to be a one parameter family of random variables where your PDF is specified by a parameter. I'll go ahead and use the notation that we had last Thursday, f of x semicolon theta, where theta is going to be your parameter. In Mathematica, though, when I put this into Mathematica, I am going to put it in with theta as a subscript. Okay, I think that'll be a little bit better to do in Mathematica. I do want to have Mathematica open, and in fact, even also have perhaps the last class's notebook open. And make a new notebook. And I think I want to quit the kernel here. I want to make sure I clear the memory here. Today is class 14. And let me also clear the memory by quitting the kernel. Oops, not that one. I don't know what happened there. Link snooper? What in the world is that? I have no idea what that is. Link snooper. Okay, maybe the kernel was already quit. Maybe I already did it. Okay, yeah, I must have. Okay. Anyway, coming back to the example. The domain where the PDF is going to be positive is going to be 0 to 1. Pretty simple domain. And the formula we're going to use in terms of the parameter theta is theta times x to the theta minus 1, where theta goes between 0 and 1, and 0 otherwise. I don't know that we'll need it, but this would, of course, mean the CDF. If you think about it here, if you wanted to write down a formula for the CDF, capital F of x theta would, of course, be 0 if x is less than or equal to 0. Excuse me. The integral of this thing with respect to x when x is between 0 and 1. Imagine integrating that, you're going to get just x to the theta, right? because the derivative of x to the theta would be theta. X to the theta is -1. And 1 if x is greater than or equal to 1. That would be the CDF, but I don't know that we're going to need that. This is a PDF. I mean, obviously the CDF, you can see, goes to 1 as x goes to 1 from the left. As x approaches 1 from the left, x to the theta is going to approach 1. 1 to the theta is 1. This is a valid PDF. Let's start by, again, getting practice with method of moments and maximum likelihood. Let's go ahead and do the method of moments, even though mostly we're going to focus on maximum likelihood in these next 3 or 4 class periods. Just to review method of moments and to see that it gives a different answer, as you might expect in strange situations like this, than maximum likelihood does. If we're going to use the method of moments, we need to figure out the first moment. So we need to integrate x times the PDF over the domain where the PDF is positive. Multiply this function by x, you're going to get theta times x to the theta. Do that integral, theta is a constant. You're going to get theta over theta plus 1, x, oops, that's a 1 there. X to the theta plus 1, evaluated from 0 to 1. 1 to the theta plus 1 is 1. 0 to the theta plus 1 is 0. This is going to give theta over theta plus 1. That's the expected value of x in this context. You could call it mu if you like. What's the goal based on this? The goal is to use method of moments and maximum likelihood to find estimators for theta. Question?
Should the amount of PDF be, why is that one theta and then the CDF is x? Between 0 and 1 on theta on the PDF?
Oh, mistake. Sorry. That should be an x. Theta can't be negative. Theta does have to be positive, but that's the only restriction on theta. Okay, so how do you do the method of moments? When you got this equation relating, in this case, the first moment to the parameter, like you see, replace the theoretical moment, the expected value, with a natural estimator for it, x bar, or if you prefer M1, and replace theta, the parameter, with theta hat, the symbol for its estimator. I'll go ahead and just use an x bar here. So I'm using method of moments here, M.O.M. Method of moments, replace e of x with x bar, replace theta with theta hat, and then just solve for theta hat. It's an algebra equation to solve. It's just a logical method for trying to estimate theta. Is it a perfect method? Well, not necessarily. Multiply both sides by theta hat plus 1. Solve for theta hat. So subtract theta hat from both sides and also subtract x bar from both sides. Here I can factor out a theta hat. This is theta hat times x bar minus 1. Divide both sides by x bar minus 1 and then negate the top and the bottom, and you would get theta hat equals x bar over 1 minus x bar. So I did 2 steps there. I first divided both sides by x bar minus 1, and then I took the resulting fraction and multiplied the top and bottom by -1. So I don't have to worry about the negative sign on the top. So there's the method of moments estimator for theta. It is a statistic, right? That's a function of the random sample. It's a random variable. Statistics are random variables. It's by this logic here, it's a natural thing to use to estimate theta. We might wonder if it's an unbiased estimator for theta. We might wonder, is it a consistent estimator for theta? Is it efficient? Remember, unbiased, consistent, efficient, those are words we've talked about recently. Those are hard questions, actually. Let's skip them for the moment and do the maximum likelihood. Maximum likelihood estimator, and see if we get something different. So this again is going to be more important for our goals in these next few weeks, because in getting to the name and Pearson lemma and likelihood ratio test, we need to think about likelihood functions again. The likelihood function, we're given, remember, data, observed values of X from a random sample, X1, X2 through Xn. Notice these are little x's. The likelihood function L of theta is the product of the PDF values. Use your capital Pi product symbol, little f of x sub I, semicolon theta. This is a function of theta because the little x sub i's are fixed. I'm not saying what they are, I'm just saying they're fixed. And the method of maximum likelihood says to try to find the maximum likelihood estimator for theta, find the value of theta that maximizes this likelihood function. Use calculus to maximize this. It is a function of theta. Take its derivative, set it equal to 0, solve for theta. Unfortunately, remember, typically doing it this way is a difficult thing to do because you got a product of a bunch of things. You'd have to use the product rule n times. Yeah. It is possible. It's just not so nice. So instead, we maximize the log likelihood function. LL of theta, natural log of L of theta, because logarithms convert products to sums. Before I do so, maybe I should write the formula for the PDF in here where it's positive. I'm assuming all these x's are between 0 and 1 for this example. And based on the formula for the PDF in that case, you got a product of a bunch of expressions that look like this, theta times x sub I to the theta minus 1. So I'm taking the log of that product, ln of this thing, by properties of logs, that's going to be the sum of logarithms of these things, because the log of a product is the sum of the logs. And within each of those, I also have products. Ln of a product there is also still the sum of the logs. And I can also, when I take the log of the second term there, the second factor here in that product, another property of logs allows me to bring the theta minus 1 in front, right? Theta minus 1 ln of xi. The sum can be broken into two pieces. The first of which is the summation of ln of theta as I goes from 1 to n, but with respect to the summation, there's no i's there. That's a constant. You just get n times natural log of theta. With the second term there, the theta minus 1 doesn't involve an I. That can be factored out. Theta minus 1 of the summation. I still need the summation there for the natural log of the xi's though. So there's the log likelihood function. If I can find the value of theta that maximizes the log likelihood function, That's the same value of theta that's going to maximize the likelihood function. But it's much easier to differentiate this. Log likelihood prime of theta with respect to theta, n is constant. Differentiate the first term, you get n over theta. Differentiate the second term with respect to theta. It's a linear function of theta. The derivative is just the coefficient of theta, which is just the summation, in fact, if you imagine distributing it through the parentheses there. There's the derivative, set it equal to 0. Solve for theta. It seems like we're going to get negative signs. And then we're not going to be able to get rid of the negative sign. Will that work out okay? Shouldn't theta be positive? Well, remember these x's, these xi's are between 0 and 1. So their natural log is negative. This is actually a positive quantity here, even in spite of the negative sign, because the x's are between 0 and 1. Solve for theta. Divide both sides by the summation, multiply both sides by theta. You'll get theta is, and also multiply both sides by -1. Negative n over the summation, I goes from 1 to n, of natural log of xi. That would be the most likely value of theta. I could call it theta hat right away, although I'm using little x's, so it's more like an observed value of theta hat. As an estimator, as a theoretical random variable, I could write theta hat equals -n over the summation, I goes from 1 to n, of the natural log of capital Xi. As an estimator, a theoretical estimator. We definitely got different answers, right? Method of moments gave us x bar over 1 minus x bar, a much simpler estimator. Method of maximum likelihood gave us a more complicated estimator, different, more complicated, not necessarily worse, just more complicated. It's hard to say ahead of time which one's better and which one's worse, or if they're, or whether they're both unbiased or not, or whether they're at least asymptotically unbiased, or if they are unbiased, whether they're consistent or efficient, which one's more relatively efficient. Those questions are not so clear at all, because, for example, to even think about whether one of these is unbiased, you have to take their expected values. We don't have nice formulas for expected values of ratios. Could it be done? I thought about it before class, and I think it could be done. It's just not easy. So let's go ahead and use Mathematica to confirm some of these things, or at least simulate these things and see if the simulations confirm the theory. Again, the simulation is good for a couple different things. One is just to confirm that the theory you're trying to do seems to be right. It's not a proof, but it seems reasonable at least. And another thing simulation is good for is when the theory is just too hard and you just don't know what else to do, like with chutes and ladders. So yeah, I'm going to go ahead and put the theta as a subscript here. I came away this morning with impressed enough with the power of Mathematica here that, even though on the job, most of the people you're going to encounter are used to spreadsheets, R, maybe Python, I'd encourage you to keep seeing if your employer can let you use Mathematica, because I'm kind of doubting that R at least can do what I'm about to show you. Maybe Python could be programmed, but I'm not so sure about R. What I'm showing you right now is pretty basic. Probably R and Python can do this, but I'm going to use the convolution operator in Mathematica, and I was very impressed that what it was able to do. Remember in Mathematica, the otherwise, you don't put the word otherwise, you put true. Kind of a strange thing to put, but that's what you do. So there's our PDF. Perhaps we could not worry about doing it as a piecewise, but it still ends up working. So I'm going to go ahead and do it that way. Remember, it's probability distribution that allows you to do simulations with user-defined PDFs. And escape SCD makes a cursive D. Not that you have to make a cursive D here, but it's pretty. Okay, so probability distribution is what we wanted to use. Probably will have you do some Mathematica for your next assignment here. Similar to what I'm showing you here. F sub theta of x. X goes from 0 to 1 is the domain where the PDF is positive. That needs to be put in there. You enter this, it seems to not do anything. Well, it did do something. You just can't see anything. There's no output. If I want output, for example, if I want to know the mean of this probability distribution, I need to type mean and then put the SCD of theta in there. Actually, I didn't test this out for a general theta. Let's see if it works. Yep, it does. And confirms our by hand answer, right? Theta over theta plus 1. Actually, I was doing the variance within it with integrals. The variance is not very simple. The variance is kind of complicated looking. In fact, it looks like it's taken a while to compute it. I did it with an integral. Okay. It could be that it's just making it too hard on itself because Mathematica often defaults to assuming numbers are complex numbers. All right, let's go ahead and abort that. I wonder, sometimes when you add something like this here, although I forget the syntax, assumptions, reals perhaps, might make Mathematica assume theta is real, but it looks like that's still stalling. Okay, let's go. I'll go ahead and compute the variance with integrals. It can do it with integrals. Although you will see it assumes theta is a complex number in this case. Takes a little while, but it does compute it. I did it beforehand. I'm almost, yep, there. Oh, okay. I must have just plugged in this. If the real part of theta is greater than -1, then the integral converges and converges to this. But of course, for us, theta is a real number bigger than 0, so that's definitely true. There's the first moment, confirms the mean. Second moment gives you this. And second moment minus first moment squared is complicated. In fact, the bottom of the fraction is a cubic function of theta. So it's not a simple variance. That's the variance. Square root of that would be the standard deviation. Let's go back to simulation though. Once you've got probability distribution used to define your probability distribution, then you can use random variate. Use the d theta. There is one observed value. I need a value for theta. Let's let theta be 5, for example. Let's try 4. There's an observed value, a bunch of observed values. Or if I want to say 100 of them, there's 100 of them. What's the PDF look like when theta is 4? There it is. Left skewed distribution, long left tail, but because the PDF's higher, close to 1, most of the data is going to be close to 1. The mean is going to be close to 1. 4/5. You might wonder also, how does theta affect the graph? I could make a manipulate. Probably need to keep the plot range fixed to make it nicer. There's when theta is close to 0. There's actually a vertical asymptote when theta is close to 0. Think about the formula. If theta is 0.1, this is 0.1 times x to the negative 0.9. 1 over x to the positive 0.9. There's going to be a vertical asymptote at 0. When theta gets up to 1, then there's no vertical asymptote anymore. But if theta is just barely bigger than 1, you got a vertical tangent at the origin, like a square root function. It's only when theta is bigger than 2 that it looks a little bit more normal. Like that. So when theta is close to 0, it's a right skewed distribution, and the mean would be close to 0. Theta over theta plus 1 is close to 0. When theta gets bigger, theta over theta plus 1 approaches 1. The mean approaches 1 as theta gets bigger and bigger. What's my goal? My goal is to try to confirm that these estimators seem good. Method of moments estimator, x bar over 1 minus x bar, and the method of maximum likelihood estimator, this thing. Are those good estimators? Do they seem to be good based on simulation? Do they seem like they might even be unbiased? It's hard to say for sure. Okay, let's go ahead and use M.O.M. M.O.M. is defined to be x bar over 1 minus x bar. Mean x bar, or no, data. I should call it data. Here, let's do data sub theta. Let's change that to a theta. So this will be M.O.M. sub theta. Mean of data sub theta over 1 minus the mean. Right? That was our method of moments estimator right there. Can you see it? X bar over 1 minus x bar. All right, Mathematica, what is M.O.M. of 4? When theta is 4, what's M.O.M. of 4? Should be close to 4. Oh, I thought it would work. Oh, I didn't use an underscore. Okay, not too far away. Yeah, okay, generally close to 4. If theta were 3, is it close to 3? Yeah. If theta is 1/2, is it close to 1/2? Yeah. This is helping me believe this is a good estimator. It's not a proof that it's unbiased or anything. But it's not doing too bad. I could try to make a histogram to see if it seems close to unbiased over many, many simulations. I could also see if it seems consistent, like if maybe if I make my simulation more than 100 data points, say 1,000 data points instead, is it generally closer to 0.5 in this case? Is it, if I change the theta to a 4, is it generally closer to 4? Yeah, I think so. We could go the other extreme and go to sample size 10 and see if it seems less consistent. Yeah, there's some farther away ones. Let's go back to sample size 100. So there's the method of moments estimator values. How about the method of maximum likelihood? Need to compute those things. M.L.E. Maybe I should have used all capital letters. Okay, how about M.L.E. of theta? It depends on n too, right? Depends on the sample size. Here n is 100. I could make this depend on n. I'm not going to bother. I'll just put 100 up there. Don't forget the negative sign. Summation, I goes from 1 to n. N is 100. All the logs of the xi's, the data values. We can access those data values with this syntax. Although I guess I need a theta, don't I? Okay, data sub theta. What's M.L.E. for? Hopefully close to 4. Hey, yeah. Do it again and again. It does other simulations. Yeah, they're all close to 4. I did find that this slowed down if you use a smaller value of theta. 0.5. It takes a little longer. Not sure the reason. The logs, yeah, I think sometimes your data is going to be pretty small numbers when theta is close to 0. And then when you take the log of those, you end up with big negative numbers. That might be part of the reason. I thought it wasn't this slow though. Okay, let's abort that. I wonder if that was it. Maybe it doesn't like the decimal point. Is that possible? Okay, there wasn't too terribly long. Let me try 1/2. Okay, that was quicker when I used a fraction. Okay, so it's getting close to 1/2. If we had to try to figure out if something like this, let's take the simpler one. If something like this were unbiased, for example, could we do it? I've never done it before. I thought about it for about 5 to 10 minutes this morning and used Mathematica to see if I could get Mathematica to help me a little bit. And amazingly, I could. And that was where I was amazed by Mathematica. It was not a full proof of it or anything, but it was enough help with Mathematica that I believed that it was maybe possible. You know, what if how would you figure out the expected value of this thing? Again, there's no simple properties for expected values of fractions. You can't use the expected value of x being mu to say this is like mu over 1 minus mu. Which would equal theta, I think, by the way. Mu over 1 minus mu here. This is mu. But I don't know that you can do that. At least I don't have a proof of that you could do that. So you'd have to try to figure out the PDF of theta hat and integrate theta times that PDF if theta is the variable. You could call the CDF, you could try the CDF method. Okay, so this is just ideas about finding the expected value of theta hat from the method of moments, which would be the expected value of X bar over 1 minus X bar. It's not going to be finishing those ideas. What's the CDF? Use the CDF method, in fact. You could call it capital F sub theta, theta hat maybe, of theta, little theta, make it a little theta. Be the probability that capital theta hat is less than or equal to little theta. You got to relate it to the distribution of X bar. That's the point here. Solve that inequality for X bar. That sounds like a helpful thing to do. Multiply both sides by 1 minus X bar like this, which does not change the direction of the inequality because X bar is going to be between 0 and 1 for this example. So we don't have to worry about multiplying both sides by a negative number there. And this is theta minus theta times X bar. I could then add theta times X bar to both sides. And then I could factor out the X bar. And then divide both sides by 1 plus theta, which is also positive, so it doesn't change the direction of the inequality. One plus theta is bigger than 1, which is positive. Theta is bigger than 0. And then that's good because that's going to relate to the CDF of X bar. Plug in theta over 1 plus theta. But that would mean I'd need to know the CDF of X bar, or if I differentiate now to find the PDF, little f sub theta hat of theta would be the derivative of capital F sub X bar of this, which would be little f sub X bar, the PDF of X bar, evaluated at theta plus 1 over theta times by the chain rule, the derivative of theta over 1 plus theta. I'm differentiating with respect to theta. And I need the quotient rule for that. Low d high minus high d low over the square of what's below. This up here simplifies to just a 1. Right, the thetas cancel. So it looks like it's the PDF of X bar evaluated at theta over 1 plus theta divided by 1 plus theta squared would be the PDF of theta hat. And you'd have to integrate theta times that thing to get the expected value of theta hat. And it would be an improper integral because theta goes from 0 to infinity. Yikes. Yikes. But maybe doable, maybe. You can't completely rule it out if you could find the PDF of X bar at least. And that's where Mathematica kind of astonished me. Even when F sub theta was entered in a piecewise way, like it was here, Mathematica was able to give me hope that it could be found, that this PDF could be found. Now, of course, by the central limit theorem, if n is large, X bar is approximately normal. And so maybe you could use a normal approximation there. It wouldn't be exact, so that's still a problem. You could use the PDF for a normal curve there, perhaps, to at least try to approximate this expected value. But that still would be plenty complicated, and I don't know if it'd be doable or not. I haven't tried it. It's hard for me to imagine trying it. It's an improper integral. You'd have to do limits. Yeah, I have no idea if it's possible. And I actually have no idea if what I'm about to show you is really possible, but I was still impressed with Mathematica's ability. And what am I talking about here with Mathematica? I'm talking about Mathematica can do convolutions the built-in command is called Convolve, I believe, Convolve. Convolve gives the convolution of two functions. And I was impressed that Mathematica was actually able to convolve here with this piecewise example. Remember what we talked about recently since spring break. If you want to find the PDF of a sum of two random variables that are independent, we are assuming independence here, by the way, because we got random sampling. That can be found by doing the convolution of their two PDFs. Now, means are not, the mean of x bar is not x1 plus x2. It's x1 plus x2 divided by 2, if n is 2. It's not x1 plus x2 plus x3 when n is 3. It's x1 plus x2 plus x3 divided by 3. So you've got to divide by n, which means what I'm about to show you is not the exact way to do it, but I was still impressed anyway. Convolve f sub theta of x with itself, for example, is going to give you the PDF of essentially x1 plus x2, if you imagine that's a random sample of size 2 from the distribution of x. Call its variable w, say you got to put a w in the last spot. Now, I think I tried this with a particular value of theta. Let's see if it works with the general value of theta. It may not work with the general value of theta. Give it a few seconds here at least. It worked, although it's messier. It involves the beta function and the gamma function. Okay, let's use a particular value of theta like 4. And then it's something simpler looking. And it looks like what we did with integration examples last week. Right? These piecewise functions, we kind of got these kinds of things. And Mathematica was even able to, so this is supposed to be the PDF. If you wanted to find the CDF, essentially an antiderivative of that, although you'd have to make sure its value at 0 is 0. And yeah, that has a value of 0 at 0. It's piecewise. It's doing a piecewise, integrating a piecewise function piece by piece. They may want to confirm that the mean is right, perhaps, for the sum. Now, remember, when theta was 4, the mean was 4/5, right? For the variable itself. This is supposed to be the PDF of the sum of the variable with itself. So its mean should not be 4/5, but should be 8/5, 4/5 plus 4/5. Okay, we need to do a definite integral, sorry. Definite integral from 0 to 1. W times the PDF. Yeah, that whole thing. W. Oh, 0 to 2, excuse me. There we go. 0 to 2. W goes from 0 to 2. If each observed value of x is between 0 and 1, then the sum is between 0 and 2. This is what amazed me. And you can even go further. You could even, for the sum of 3 of them, x1 plus x2 plus x3, you could even convolve the convolution. Copy. And paste it here. Let's see, how should I do this? I should probably use a dummy variable in here and call this its ultimate variable x here. This is going to be the PDF of x1 plus x2 plus x3. And it works. And you can integrate it to find the CDF. And you can integrate W times it from 0 to 3 in this case now to get the mean. Should be 4/5 plus 4/5 plus 4/5, 12/5. Yay. Okay, this is going to be a problem though if you want to do it for a general n, right? We did it for n equals 2 and 3 here, but how do you do it for a general n? Mathematica, I'm sure, couldn't do it because you don't specify n yet. Maybe there's some theoretical way to do it. I haven't run across it, but I'm still impressed. Okay. Theory is not easy, but if you study it long enough, you can do it. And hopefully avoid mistakes too. Okay, so I thought that was kind of fun. For the rest of the class today, which is only, what, 25 minutes now. I was hoping to do a lot about confidence intervals and hypothesis testing. I think we better just focus on hypothesis testing if we really want to get to the Neyman Pearson lemma, even starting on Thursday a little bit. Because the Neyman Pearson lemma is really about hypothesis testing, not confidence intervals. Let me put it this way. You should still read about confidence intervals and be able to use the formulas. Now, confidence intervals are easier, at least as far as using the formulas go. Their derivations are maybe sometimes a little suspect, perhaps. The derivations of the formulas for the confidence intervals. I think I do want to talk about those derivations to some degree, maybe on Thursday, not today. So read the stuff about confidence intervals, including reading the derivations of the formulas for the endpoints or for the margins of error. So I think I will probably talk about that a little bit to some degree on Thursday, maybe next Tuesday. And I probably will assign some homework problems where you at least compute confidence intervals. But that's relatively easy, right? You've done that before. It's not too bad. Well, it'd be more important if you want to make the Neyman Pearson lemma and likelihood ratio test our end goal here before we do categorical data, chi-square test, and get to exam 2, is we better focus more on hypothesis testing. Now, in chapter 8, hypothesis testing is introduced in the context actually of a situation where you're testing the probability of success P for a binomial random variable, which is great. And you should definitely study that. But I think more commonly, we're going to think about more in terms of testing means. So your generic right-tailed test, say, for a population mean, looks like this. You got a null hypothesis. Haven't done any hypothesis testing yet this semester, but you've done it before. Null hypothesis. It's typically written mu equals something. Technically speaking, you should write the alternative hypothesis first. Really, that's your research hypothesis. And if it's a right-tailed test, it's typically that mu is, well, for right-tailed test, it's that mu is bigger than some number, mu sub 0, say. Technically speaking, you could argue that the null hypothesis is the complement of that. If the alternative is that mu is bigger than mu 0, then the null would be that mu is less than or equal to mu 0. However, we almost always keep the null hypothesis as a simple hypothesis, mu equals the null value, mu 0. Maybe I'll write technically mu is less than or equal to mu0, but we almost always write it as a simple hypothesis, the equality using an equal sign makes this a simple hypothesis. And that's good enough. For reasons I'll get into, to consider the null hypothesis to be a simple one. Effectively, whatever you want to do is good enough in that case. We will actually consider situations, unlike what we did in problem stats here in these coming days, where the alternative hypothesis is not a simple, a simple hypothesis instead of a non-simple composite one like this. But this is what we mostly did back in problem stats, is this kind of test. And remember what we did. There were two approaches. One approach was to find something called the p-value of the test. That's called significance testing. And remember in general what the p-value was. I'll just describe it in words. I'm not going to write those words down. Just to remind you, it's the probability of obtaining an observed value of a certain test statistic, like X bar, or like Z if you convert to standard normal, as extreme or more extreme as what you actually observe from your data, under the assumption that the null hypothesis is true. So you're giving the null the benefit of the doubt. You're assuming it's true. What is that probability? If it's low, if you have observed something rare when the null is true, then you say, well, that means I think the null is false, so I reject it. Reject the null in favor of the alternative. Accept the alternative. You think the alternative is true. But you might make a mistake when you do that. The null hypothesis might really be true, and you have observed something rare when the null is true. So you might make what's called a type 1 error, rejecting the null when it's true. On the other hand, if the p-value is not very small, how small is very small? You know, the typical standard was like 5%, but that's not set in stone. If the p-value is not very small, for sure, like if it's 30, 40%, don't reject the null. You don't have sufficient evidence to reject the null. It's not that you necessarily think the null is right, but you don't have sufficient evidence to reject it. So you either say we do not reject it, or you say, okay, I accept the null. But even there could be a mistake. You could be accepting the null when it's false. You could be making a type 2 error. Remember these things? Let's think about these things again, but now in the context of also including a level of significance. The letter alpha in this context is called the level of significance of the test. And if you do the test with the other method, instead of finding p-value, the p-value, you find what's called the critical region, rejection region. Alpha helps you figure out what the rejection region is. Because what alpha really represents is the probability of type 1 error. Rejecting H0 when H0, the null, is true. In a courtroom, the null is innocent, the alternative is guilty. While you go through the trial, you give the null the benefit of the doubt. That's the assumption of innocence until proven guilty. A type 1 error then is like convicting an innocent person. As a society, we typically think of convicting an innocent person as a worse mistake than acquitting a guilty person. I mean, they're both bad, but we as a society, and I think most societies generally think convicting an innocent person is worse, a worse mistake. And sort of that's sort of the philosophy behind a type 1, calling this a type 1 error, and the other kind of error, a type 2 error, is like rejecting the no when it's true is sort of considered to be worse, a worse mistake, a worse decision. It's not a math mistake, by the way. It's a mistake in your decision when you make such a decision to reject the no when it's true. Of course, in many situations, you don't really know for sure whether the null is true. That's why you're doing the test. But even after you're done with the test, you still don't know for sure whether the null is true. You just have evidence against it. You have strength of evidence against it. Is it strong evidence or not so strong? Let's think about this graphically. So I'm not doing calculations here. I'm more focused on concepts. Not sure if we'll have time for calculations or not. We'll see here. What I want to draw, I want to make some graphs. I want to draw, first of all, a number line. On this number line, draw a point. This point is going to represent the null value, mu sub 0. Right, that's the null value. It's a particular number. Could be 10, could be 20, could be 37.2. Remember, X bar is an unbiased estimator for mu. We also have the central limit theorem that says that X bar is approximately normal when n is large, even if the population is not normal. Although some extra special theorems apply that actually that X bar is exactly normal, not just approximately normal, but exactly normal when your population is normal. That was something sometimes called the cornerstone theorem in chapter 7, before the central limit theorem. This Dr. Wetzel and I have called the cornerstone theorem. It's important, though when you apply it in real life, it's always sort of applied approximately. If you got a random sample of size n from an exactly normal distribution with mean, mu, and variance sigma squared, then X bar, the sample mean, is exactly normally distributed with mean, mu, and variance sigma squared over n. This is a theorem that can be proved if you're assuming you are sampling from an exactly normal distribution. When you apply the theorem, though, in real life, you might argue that it never applies exactly, because how can you ever know for sure that you have an exactly normal distribution? No doubts about it. So it's really more of an approximate application of a theorem in real life. Sounds funny, but that's really what's going on. It's got mean mu. That's true no matter what, as long as you're doing random sampling, whether the background distribution is normal or not, because X bar is always unbiased. And in fact, the variance always equals sigma squared over n in general. The new thing is that it's normally distributed. So I want to draw a normal distribution here. And what is this normal distribution supposed to represent? It's centered at mu 0. It's supposed to represent the distribution of X bar. Often not just called the distribution of X bar, but for emphasis called the sampling distribution. I'll put the word sampling in there with, say, in parentheses, sampling distribution of X bar. Some of you know from helping out in math lab, then in statistical analysis, we usually do call it the sampling distribution to emphasize that it comes from a random sample. X bar is a statistic. computed from a random sample. So certainly we can just call it the distribution of X bar, but for emphasis, for conceptual educational emphasis, we call it the sampling distribution. And it's not just for education's sake. People out in the work world will call it a sampling distribution as well, because that's what they were taught. Most people, even who use statistics, are not taught statistics at this level. They're more taught like a business stats course, and their teachers use the word sampling distribution back there. X bar is unbiased. This is the same as the mean of X bar. And the standard deviation of this sampling distribution, which looks exactly normal if this population is normal and approximately normal, even if the population is not normal, is this horizontal distance between the vertical line there and this inflection point. And that distance will be the variance of X bar, or the standard deviation of X bar, excuse me, sigma sub X bar. And that'll be the square root of the variance of X bar, the square root of sigma squared over n, which simplifies to sigma over square root of n. And when you decide on the level of significance for a test, what you're really doing is you are defining something called a rejection region or critical region. Both names are used. Critical region is sort of the more general name. People use the word rejection region to emphasize we're using it for deciding when to reject the null hypothesis. And for a right-tailed test, it's going to be a region to the right of some number, some critical number. What should I call it here? How about X sub alpha? Okay, that's an X, it's not a chi. My cursive X's look like chi sometimes. But X sub alpha, the area to the right of that is alpha. And that is the probability of a type 1 error, because this is going to be the rejection region. The values of X along the number line to the right of X of alpha are going to be the values of X that lead to rejecting the null. So we call it a rejection region. We also call it a critical region because it is critical for solving the problem, you might say. And the boundary point there is sometimes called the critical point or critical number or critical value. Rejection region or critical region. If we get an observed value of X bar based on a random sample of numbers, talking data here, in this region greater than or equal to X sub alpha, which some books call X sub crit for critical point, then we will reject the null hypothesis. And if we don't, then we fail to reject the null. We can say accept the null. Remember doing that? These ideas? Standardization, converting to Z, means we can also think about these ideas in the context of a standard normal distribution. We can also draw a corresponding standard normal curve N01 centered at 0, and the critical point is going to correspond to Z sub alpha, which, you know, if you only have the table, you can look up in the table. That area equals alpha, and this is the rejection region or critical region in terms of Z. You can think of it either way. And how do you convert to Z here? As always, take your variable or your data value, your observed value of X bar, I should say, if you have data. Subtract the mean of the distribution, which is assumed in the null hypothesis, and divide by the standard deviation of the distribution. The formula connecting these in the random variable form is capital Z equals capital X bar minus mu sub 0 over sigma over square root of n. Right, you've done these calculations before. I probably will assign a few problems where you have to calculate these things. It's easiest to figure out the rejection region in terms of Z first. And therefore, it's typically easiest to do this first and decide whether to reject or not based on the value of Z. This is your test statistic for the test. I mean, you could call X bar a test statistic as well. But the test statistic we typically talk about using is after you convert it to Z. When we think about the rejection region in terms of Z. So for example, if alpha is 0.05, Z sub alpha is Z sub 0.05, that should be 1.645 if memory is serving me correct. Let's use technology. Inv norm, right? We're after effectively percentiles here. We're after the 95th percentile there. 0.95, mu is 0, sigma is 1. Yeah, about 1.645, I guess, right. It rounds closer to 1.64. If you use the table, you see you typically either round to 1.64 or 1.65. But if you want 3 decimal places of accuracy, 1.645 is what to use there. So if alpha is 0.05, if it's a 5% level of significance for a right-tailed test, you'd reject the null if the observed value of the test statistic is greater than 1.645. And you'd fail to reject if it's less. What if it equals? It's up to you, I guess, if it equals it. I guess I would say as a default, go ahead and reject it. I mean, if it's close to the boundary, it's not really clear cut one way or the other, and maybe it doesn't make a big difference one way or the other, but yeah, reject the null if the observed value of Z is greater than or equal to 1.645, fail to reject if it's not. I think with our remaining few minutes here, I still don't want to do an example, but you should be able to for your homework. Instead, I want to talk about type 2 errors, probability of a type 2 error, and a power of the test here in just a few minutes. A type 2 error is when you fail to reject the null when you should have, because the alternative is true, meaning you failed to convict that guilty person. Beta is the probability of a type 2 error. Fail to reject H0 when H0 is true, or excuse me, is false. H1 is true. Another important quantity is called the power of the test. It's 1 minus beta. It's the probability of doing what you want to do as a prosecuting attorney. If that person's really guilty, you definitely want to be able to convict them. Do you have power to convict them? Probability of rejecting H0 correctly when H1 is true. doing the opposite thing. You're not making a type 2 error there, you're doing the opposite thing. That's supposed to be in H1. Ignore that dot there. As these things are stated, they're not well defined. Because what does it mean that H1 is true? It's not a simple hypothesis. There's lots of different things that mu could be if H1 is true. Infinitely many numbers, in fact. So these are not well defined. So to compute them, you have to decide on a value of H1, which brings up a practical question of how to decide, which we won't talk about today. In just 1 or 2 minutes here, instead, we will just focus on the picture again. So here again is the sampling distribution of X bar if the null is true. But if the alternative is true, that's not the sampling distribution of X bar. If the alternative is true, if mu equals, say, mu1, that alternative is true, then the sampling distribution of X bar looks more like this, centered on mu1 instead of mu0. The rejection region is still the same. There is still some value X crit or X sub alpha, I'll call it X crit, where you reject in the null based on this area under the green curve being alpha. That's still the same, because you still have the same null hypothesis. Making a type 2 error, failing to reject the null when it's false, so you should have rejected it, means you were not in the rejection region. X bar was less than X crit. But if this alternative is true, if mu equals mu1, then the probability of that happening is going to be this area under the red curve to the left of X crit. That area equals beta. And therefore, this area over here under the red curve is the power. And the goal is to make both alpha and beta small, or said another way, make alpha small and the power big. How do you attain that goal? One way to attain it is make mu1 further away from mu0. But is that right? Is that best? Another way is keep mu1 where it is, but maybe make the sample sizes n bigger, which makes these curves skinnier. Though that does affect what the rejection region is, so you have to recompute the rejection region. We'll get into some computational details on Thursday before we keep moving toward the Neyman-Pearson lemma. Have a good day.